Operations begin at dawn as the aircraft initiates a long-range trajectory across the border regions.
The navigation system plots a course spanning over 1,000 kilometers to reach the industrial infrastructure.
Skilled operators utilize advanced night vision technology to navigate effectively in low light conditions. Maintaining a low altitude, the unit maneuvers carefully around critical power infrastructure.
Precise telemetry allows for real-time adjustments via handheld interface units.
Whether from stationary posts or mobile units, crews remain focused on the navigation data.
Digital tracking systems monitor the formation as it coordinates across specific regional sectors. Ground teams rapidly assemble the hardware while pilots prepare for immersive remote operation. Once airborne, the aircraft proceeds along its designated path under constant human supervision. Sensitive control inputs allow the aircraft to execute complex banking maneuvers with stability.
Approaching the destination, the unit begins a calculated descent, guided by thermal sensors.
High-resolution feeds provide operators with detailed surveillance of vehicle depots on the ground.
The operational scope extends across multiple territories, requiring constant logistical coordination.
Field personnel utilize radio channels to synchronize movements and verify system status.
Advanced radar arrays continuously scan the airspace, feeding data to internal monitoring stations.
The system calculates distance and trajectory by analyzing signal reflections from airborne objects. Operators undergo rigorous simulation training to master the complex tracking interfaces.
Visual confirmation remains a key component, utilizing both cockpit views and ground optics.
Legacy analog systems work in tandem with digital interfaces to verify coordinate data.
Heavy aerospace engineering provides the propulsion and payload capacity for defensive measures.
Information relays ensure that command posts remain updated on the aircraft's progress.
Mobile defense units patrol the perimeter of critical industrial storage facilities.
As the aircraft executes its final maneuver, remote screens capture the telemetry.
The operator in the immersion headset analyzes the incoming data stream in real time.
Training centers prepare personnel to manage the airspace and track multiple variables.
The aircraft emits navigation signals, mapping the terrain contours electronically.
By reading the signal return from the ground, the system adjusts altitude automatically.
Internal combustion engines provide the necessary range to traverse the thermal landscape.
The pilot maintains a steady course, interpreting the thermal data from the onboard sensors.
Field assembly is streamlined, allowing rapid deployment of the modular airframe.
Technicians carefully configure the internal wiring to ensure system connectivity. A coordinated group of units is tracked digitally as they cross regional boundaries.
Mobile radar units relocate to maintain coverage of the active airspace.
Scanning arrays rotate continuously, while operators interpret the incoming positional data.
The flight path is monitored closely as the aircraft navigates deeper into the region.
Logistics teams navigate the terrain to position the tracking equipment effectively. Strategic flight planning utilizes multiple altitude layers to optimize operational efficiency.
Telemetry confirms the aircraft is maintaining its assigned altitude profile.
Optical sensors struggle to maintain a lock on the agile aerial platform.
Thermal imaging provides a clearer signature against the cool background of the terrain.
The airframe is designed to carry a specific payload, secured beneath the fuselage.
A rocket system is deployed, ascending rapidly to intercept the flight path.
Radar operators continually assess the trajectory of both the aircraft and the projectile.
Fine-tuning the instruments ensures the signal remains locked on the target.
The control team remains vigilant, monitoring system performance from their station.
Navigation continues uninterrupted as thermal sensors guide the unit through the night.
The lightweight aerodynamic profile stands in contrast to the heavy ground-based systems.
Schematics illustrate the engagement geometry between the ground unit and the aerial target.
The launch sequence is initiated, propelling the interceptor towards the calculated coordinates.
The projectile tracks its target while additional aerial support prepares for takeoff.
The aircraft is equipped with a specialized radar array housed within the nose cone.
This technology allows the pilot to scan for targets at distances exceeding 300 kilometers.
From the cockpit, the pilot scans the horizon, searching for the smaller aerial signature.
The two aircraft converge in the same airspace as the search continues.
Pilots execute tactical maneuvers to position themselves for visual identification. A pair of jets maintains formation while patrolling the sector for the drone.
The search zone is clearly defined on the digital map, guiding the aerial assets. Remote operators navigate their units through the designated sector, monitoring their progress.
Ground-based radar systems work to acquire a signal lock along the calculated route.
Deployable antennas are raised to maximize signal reception and tracking capabilities.
Technicians manage a complex array of switches to filter and analyze the signal.
The crew coordinates their efforts within the control station to maintain the track.
While the radar scans, the remote pilot makes continuous adjustments to the flight path.
System parameters are constantly tuned to optimize the clarity of the tracking data.
Precise calibration of the instruments allows for accurate telemetry of the aircraft.
The aerial unit navigates past stationary ground defense systems positioned in the field.
Schematic analysis simulates the calculated trajectory for a potential interception.
The diagram illustrates the proximity of the projectile as the drone continues its course. Radar systems verify that the aircraft remains airborne and on its trajectory.
Inside the control room, the team maintains surveillance of the system's status.
Operators make manual inputs to the control systems to refine the tracking data.
Specialized units deploy electronic signal equipment to disrupt navigation.
The aircraft utilizes the tree line to mask its signature from the electronic signals.
Technicians manage the signal frequency to maintain a clear connection.
The Radar continuously sweeps the sector while ground teams communicate status updates.
The signal units remain deployed as the aircraft navigates through the thermal environment. Thermal sensors clearly distinguish the aircraft's path against the terrain.
The unit maintains a steady course, verified by both thermal and visual observation.
The flight path terminates at the large industrial storage complex.
Navigation systems guide the unit on its final vector towards the urban industrial zone.
Digital tracking monitors the approach of multiple aerial units towards the designated area.
Localized defense systems scan the sky, ready to track any incoming aerial traffic.
Optical sensors and radar arrays work in tandem to acquire a lock on the target.
The system's tracking mechanism physically rotates to maintain alignment with the object.
The defensive unit engages its systems, launching projectiles to intercept the flight.
Smoke trails mark the complex trajectory of the intercepting rocket.
Sensor displays highlight the position of the aircraft as a bright thermal signature.
Schematic diagrams are cross-referenced with the thermal events recorded by the sensors.
Simulations depict the system's capacity to engage multiple aerial targets simultaneously.
While the automated system stands guard, the pilot continues manual navigation.
The active radar continues to sweep the sector, elevating the launch tubes for engagement.
Rapid-fire ballistics are deployed, creating a visible pattern on the sensor display.
Despite the defensive measures, the aircraft remains airborne, monitored by the crew.
The mobile unit maneuvers across the terrain while simultaneously discharging its weapons.
The aircraft continues its flight path, evading the smoke trails of the interceptors. Visual schematics confirm the structural formation of the incoming aerial group.
The tracking system attempts to prioritize targets based on the formation logic.
Armored transport vehicles are also positioned within the operational zone.
Technical specifications of the armored unit are reviewed for their defensive capabilities.
The vehicle's turret design incorporates a primary cannon for ground and air defense.
Crew members inside the vehicle maintain communication with the command network. The gunner scans the airspace using the vehicle's optical targeting system.
Simulations demonstrate the engagement range and firing arc of the vehicle's cannon.
The system is tested against simulated targets to verify tracking accuracy.
Sensor feedback confirms a successful intersection during the targeting test.
Operators remain on standby, ready to utilize the vehicle's defensive systems.
The ballistic pattern is designed to create a defensive screen against aerial objects.
The unit conducts a live-fire exercise, discharging rounds into the target sector.
Specialized ammunition is employed, designed to disperse material upon detonation.
The engagement takes place in close proximity to the industrial storage infrastructure.
Monitoring teams track the trajectory of the projectiles from their control station.
Sensors track the rapid ascent of the rocket as it seeks the aerial target.
A thermal event is detected on the ground, observed by the vehicle crew.
The operator verifies the tracking data on the internal display unit.
The display registers a significant energy release, confirming an interception.
Thermal cameras capture the descent of heated debris following the event.
The system resets to scan for any additional aerial activity in the sector.
Personnel remain at their stations, ensuring the defensive screen stays active.
The aircraft continues to navigate the airspace above the defensive positions.
Digital tracking markers maintain a lock on the object as it traverses the zone.
The tracking system provides consistent positional data to the operator.
The aircraft arrives at the designated industrial facility coordinates.
Simulations project the potential outcome of a structural failure at the site.
Large-scale thermal events are recorded, illuminating the facility at night.
Infrared sensors capture the rapid expansion of the intense heat signature.
Dense plumes of smoke rise from the storage units, obscuring the area.
While smoke blocks optical sensors, thermal imaging revealed the extent of the heat.
The thermal reaction spreads across the containment area, monitored from above.
The industrial infrastructure is heavily impacted by the ongoing thermal event.
A significant combustion reaction is visible within the storage containment.
The intensity of the reaction generates a distinct signature on all sensor bands.
Atmospheric conditions are altered as the smoke plume drifts downwind.
The heat generates turbulent air currents, visible as swirling patterns on the display.
The structural integrity of the primary storage tank has been compromised.
The event persists into the evening, releasing significant energy into the atmosphere.
Flashes of light penetrate the darkness, recorded by the night vision sensors.
A vertical column of heated particulate rises from the center of the reaction.
The magnitude of the displacement draws comparisons to significant historical events.
This concludes the technical analysis of the aerial operation and the resulting industrial incident.